Ti6Al4V and Yang Hai Li from Xi'an, together with the company. And we are looking forward to your presentation with SLM manufactured titanium alloys.
Good morning, everyone. It's my honor to give this report. And my name is Wen Wilson, and I'm from NWPO, Xi'an, China. My topic today is effects of the building direction on fatigue growth behavior of titanium alloy manufactured by SLM. And there are 4 main contents in my report: 1, background; 2, sample design; 3, effects of building direction on mechanical fatigue properties. And in this part, 3 tests were performed: tensor test, fatigue test, and FCDR test. And last, some conclusions are given. As we all know, additive manufactured titanium alloy have been becoming increasingly popular in the aerospace industry. And there are many advantages for AM titanium alloy, such as good design property, weight and material saving, excellent stress and stress weight ratio, and so on. But many researchers have revealed that laminar structures can be observed in the SM titanium alloy. The mechanical property is transversely anisotropic, so it's important to study the effects of building direction. In our research, we designed 3 different samples according to corresponding standards, and the dimensions are shown in these pictures. These pictures shows the definition of building directions. For a tensor test and FCDR test, we designed 3 building directions, and for the fatigue test, we designed 2. And the red arrow is the building direction. All the samples were built by Xi'an this technology company, and the tests were carried out after post-heat treatment process. In order to study the fatigue property, the tensor stress should be obtained at first, and we performed the tensor test, and the test date is test date is shown in this table, and this is the load displacement curves. From these curves, we can it's apparent that building direction can affect the mechanical properties. And 45-degree samples has a good performance. Young's modulus of 45-degree samples is 13.74% higher than that of 0-degree samples, and the tensor stress of 45-degree samples is 6.65% higher than that of 0-degree samples. This picture shows the fracture surface of tensor samples, and from these pictures we can observe some spots on the fracture surface. And for the 0-degree samples, the spots are arranged in order, and just like this line, and this line. And for the 90-degree samples, the spots are disorganized, and for the 45-degree samples, the spots are less than the others. And then we performed the fatigue test. We used the 80% of tensor stress as a benchmark, and then the fatigue load gradually reduced, and the details are shown in these 2 tables. And in these load conditions, the effect of frequency is studied. And from the SN curves, we can get that the 90-degree samples has a good fatigue performance. This picture shows the fatigue fracture surface of 0-degree samples, and in high load conditions, and this the fracture surface is not vertical to the load directions, and there is included angles, and it's about 45 degrees, and in this condition, the heating ablation phenomena can be observed in the edge. And for the others, the area of fatigue fracture surface increase with the decrease of fatigue load, and the surface becomes more and more flat. And in this picture, we can and the crack initial site can be observed just there, and it's not clear. And this picture shows the fatigue fracture surface of 90-degree samples, and the phenomenon is similar to the 0-degree samples, but the surface smoothness is better. This picture shows the effect of frequency, and when frequency equals 20, it's just like. And when in low frequency, the fatigue fracture surface is vertical to the load direction, and we can find this arrow and this arrow. But when frequency equals 1, and there are some dots in there. Okay, and last we studied the effect of bearing direction on FCDR. In our test, delta K equals 10, and since stress loading is adopted, stress ratio I equals 0.1, and frequency equals 20. The crack was monitored with digital microscope, and the tests were carried on based on STM E647. And then the AN curves are obtained in this picture, and it's apparent that the AN curves of 0-degree sample and 90-degree samples are basically coincident, these two lines. And the fatigue crackers life of 0 and 45-degree samples is how long fatigue crackers life, and the life is 1.46 times longer than that of 0-degree samples. And based on 7-point incremental polynomial technique, the d delta K curves was obtained in this picture, and we compared our test data with two references. One is also the AM titanium alloy, this green line, and one is the traditional titanium alloy. Alloy is this one. And from these pictures, we can find that the slope of AM titanium alloys is smaller than the traditional ones, and the value of our test is lower than the others. And also in the low delta K regimes, there are some fluctuations there. And then using Ranger software, we the Paris law constancy and M are obtained in this table. The constant M represents the slope of the sketch, as the large value represents high fatigue crack growth rate. And in this picture, and the 45-degree samples have a small slope, and the value of the M value of 45-degree samples is lowest. So we can draw the conclusion that the order of the FCR is the 45-degree samples have the lowest FCR. This picture shows the fracture surface of 0-degree samples. There are some macro-variable cross-dent in the surface. And in micro In microscopes, the inclusions and poise can be observed. This is the inclusion. This is for the this is the fracture surface of 45-degree samples. The fracture surface seems to be granular, but in the microscopes, the surface smoothness is like to the 0-degree samples. This is a fracture surface of 90-degree samples. Laminar structures can be observed in this, just like this. And in the microscopes, the surface, the fracture surface is really mass, and the pores are more than this of 0-degree sample and 45-degree samples. That's some conclusions. Okay, that's the works we have done, and there are still some works ongoing. Thanks for your attention.
And we thank you very much for the presentation and keeping the time. Other questions for the moment being? Yes, please.
It was really interesting presentation. Although this particular growth of different direction has been investigated by several researchers since 3 years ago, but still it was nice to see it. I have a question. You said you post-treated the samples. What was the post-treatment? Did you use heat treatment?
All our samples was built by the company, but they keep create for us. I don't know their technique.
So, because that's really important, it can change the direction of the crack growth. It can change the fatigue life, and it's important to know if they are heat treated or not. Besides that, one of your figures that you show for fracture surface with 45 degrees, I guess there was a problem with your machine, and the surfaces touch each other. That's why you have a shiny surface, and that is not a fracture surface. So I suggest you check it again and correct it if possible.
Okay, thank you.
Yeah.
Are there further questions?
Thank you for your nice presentation. Just a question, please. The specimens were tested as given by the company, or do you change some parameters of the manufacturing procedure? Because I have done the tests that you showed in the same alloy, and I have not microporosity at all, because we have optimized the parameters that the specimens are produced. So the first thing is to optimize the parameters for fatigue life, and then you can test other things. So it's not only to check how they give us the specimens, but the better way is to, first of all, get the best specimens. That's my opinion. Okay, thank you.
Yes, thank you.
Thank you for the question. Okay, so thank the speaker again.